Hi, today I am going to present TabPert, an effective platform for table perturbation. This is joint work with Nupur, Anshul Gaurav from IIT Kanpur, myself Vivek Gupta. So what's the motivation? Current tabular NLI models suffer from hypothesis bias, annotation artifact, and are not grounded with the evidence provided as premise. So what's the consequences? We have models with poor generalization, they don't work on out-of-domain data, and if given a counterfactual data with different primary evidence as premise, they perform poorly. So what this implies, the right prediction does not imply always right reasoning. These models are not doing right reasoning. So one way of checking if the model doing right reasoning is evaluating on challenging adversarial data sets. So what's the challenge associated with creating challenge adversarial data sets, especially their annotations? What we need is the high diversity plus constraints, because the table cannot be self-contradictory. There should be diversity in the data, and all this require manual efforts. The tools which are there, for example, spreadsheets, they are inadequate. They don't work very well for tabular data. They have inefficiency and not streamlines. So they have usability and utility issues, which we'll discuss more in later. And also we don't get any insight on which methods for creating counterfactual data is effective. What are the augmented techniques which works best for creating counterfactual data? So TabPert here come to rescue and is specially built to tackle these problems. Let's look with example. So in our case, we study InfoTabs, which is a tabular inference task, where you are given a table which has a title and a key value pairs, and there are three hypotheses as is shown, which can be entail, contradict, neutral. So the hypotheses are basically true if they are entail, false, contradict, and neutral as they are undetermined. This is taken from InfoTab data set from Gupta et al. 2020. You can check at infotabs.github.io. So our annotation process has two major steps. One is the automated state, which is used for initializations, and then there's the human interventions, which basically first fix the automated tables for logical constraint, discrepancies, and then also write new hypotheses or modify existing hypotheses and also the associated labels, plus also have some metadata information as discussed later. We create three types of tables, counterfactual A, B, C, based on three different strategies. A and B have roughly equal amount of pairs, and we took the alpha 1 set for creating this. They are all balanced, and the table C has new hypothesis written, so it's pretty less, 52 pairs. So let's look at first the automated state. So in the automated state, we want to initialize the table with a new table, which is counterfactuals. Here what we do is basically shuffle table information from other table to this table, and we do this first by checking where the existing table is coming from, what is category and what is its table number. For example, this is alpha 1 test set table. It is called category ring. We are choosing the row manufacturer for now for consideration, and then we have table number, which is T73. Now there are multiple ways we can shuffle. We can shuffle from the same set, but we can also shuffle from the different set. So in our case, we shuffle from both same set alpha 1 and also from a different set called training set. We also can shuffle from different category or the same category. For example, we can shuffle from another table from the drink category, or same table some other rows, or we can even shuffle from other category like people. We can shuffle from different keys in the same category, or same keys from different table. Like for example, we can take another table and then take manufacturer key of that, which we actually did, and also we can take a different category, different table, and even a different key to do the same thing. We can even shuffle within a table. For example, if we have a table where there's director and producer, for example, the table is from category movie, then we can shuffle between director, producer, writer, and other things. So when we shuffle these things, we also want to know what shuffling is happening, because the shuffling can create violate constraints and can create discrepancies. So we want to do some kind of a rollback operation or something. So that's why we need this metadata of how the shuffling happened for each row, each values in a table. So we store that. And it's also important to analyze if this kind of shuffling is effective. For example, shuffling from different data set is much better than shuffling from the same data set. For example, alpha 1 versus train set, or shuffling from the same table versus shuffling from the different table, which one is more effective. So we can use this metadata also to analyze which ways doing things is more effective. Now in this thing, we actually replace the manufacturer from another thing, which is Atari, and Atari is actually based on metadata we get is 0, 1, 1, 0. So we store all the metadata in a bit format. 0 means same, 1 means different. And each bit, the first is data set, second is category, third is table, and fourth is key. So 0 means that it's from the alpha 1 set, 1 means it's from different category, which is game, a different table because there is another one which is for table, and the key is same as manufacturer. So you can see we know now exactly how this table is, how this metadata is coming from. Now it's good, like we have this human intervention, then we should be done for tables, but it's not true. The table can have lots of other issues. For example, there might be possible we are not able to shuffle anything because the diversity of the keys are so much that we don't find any table where we can shuffle from. For example, this knowledge, skill, offer. There can also be logical discrepancies. If we shuffle automatically, for example, the year started cannot be before the developer and administrator date of basically that test. So there is a constraint which is there. Similarly, date of birth cannot be before the born date, cannot be before the death date. So we need human intervention. So here come the TabPert. So if you first use this initialization, which is the automated stage, to create this counterfactual table, we also create hypotheses which are exactly same label as the original one. And now first we basically look for tables for inconsistency. We can add, edit tables. We can add, edit, insert values in the table. We can even drag, drop, copy values from other table, which can be original table as well as the 3 counterfactual table A, B, C. So we can drag drop between original table and table A, table B. We can also do any drag dropping between table A, table C. Similarly, we can also add new sections. For example, if you want to insert a new row or a new edit a section, or delete any section, like if you want to delete a row. So these are some of the examples how we do. We can insert a new value, we can delete a new value. So more are there in the demo video which you can check, but it has very nice user interface and easy functionality of drag and drop for deleting, inserting, and editing any values in the key. We can also add a new sections completely. We can change the keys of the sections, we can change the value of the section, we can even delete an entire section if we don't want it. And we can also, one more interesting thing, we can, if you want to see just one table at a time, so we can focus on counterfactual table A and the original table A and the corresponding hypothesis by using our focus view, by clicking on the main view and table A, table B, table C focus view on the top. Now once we have basically edited the tables, we can also edit the sentence and also the corresponding table if need to be, because we need to do concurrently based on how we write the hypothesis. And we can then also decide the label which we want to modify. We also store a metadata by using the plus sign which is there when we do the hypothesis edit, as you can see in the demonstration in the left, where we basically mark the relevant rows and also what the strategy used for basically making this hypothesis out of all the strategies which are listed. This can be modified as per the requirement of the annotator task. So in the manual stage, basically we use entered metadata by the human, which is relevant row and strategy use. We also have the final table value metadata, because once we write hypothesis, we concurrently also can change the table. So what is the edited value? Is it coming from drag and drop? It's a new addition or what? So we use this for info tabs and we give to crowdsource. And what we basically have is 3 strategies we ask them basically to do. For all the table A, we ask them to flip labels by changing the table, trying to keep the hypothesis same. So changing table is the main approach there. In table V, we ask them to basically change the hypothesis, try to keep the modified table as it is, but the labels are flipped. And table C, we basically ask them to write a new hypothesis. Now label flip work for intelligent contradiction, but what about neutrals? So in neutrals, we just give them one instruction. Basically do has much overlap with the tables, which is counterfact tables, so that neutral come as close as to entailment, but it's actually a neutral. So add some true information which overlap with the existing or previous table. Now let's look at the performance of the counterfactual data we created. First and foremost, we saw a huge drop in hypothesis only baseline. That means that the data is suffering, the model is suffering of hypothesis bias, and once you give a counterfactual data, that bias is broken down. We also find that the overall performance with all rows decreases with the counterfactual tables. However, we also find that the only using relevant rows decreases performance in both original and counterfactual table, but in counterfactual table it actually increases compared to the original table. That means, so model is actually using irrelevant rows for prediction, and that's why we just give the relevant row, the model started losing accuracy. But in the counterfactual data, that is useful and it benefit to just give the relevant row. It shows that the metadata which we have relevant row is also important. And finally, the human performance is pretty good and equally good on both sides. So we also analyze the strategies. So we find that the table change was very effective. The label flip was very effective using hypothesis thing. We also find the hyperprint and overlap was also equally effective. Next, especially the overlap was very effective for neutrals. We will find that the new hypothesis doesn't work. So that approach doesn't work. So overall utility is we have a model and customized code. We have efficient and streamlined process for table manipulation and sentence manipulation corresponding to it. We collect very important metadata which we can use for analysis later. So finally, we provide you TabPert, which is the effective platform for semi-structured tabular perturbations, which can be used to create adversarial data sets. The metadata which we collected can be used to analyze which strategy is better, and also can be analyzed of how annotations, how model is basically failing, where it's weak cases, and what are there. We request you to visit TabPert website and also check our demo video to use the platform. Thank you.